We flew Malta Peter in from Europe just last night. Malta worked with our speaker Mike Meylan for a number of years, quite a long time ago now, so it was a very appropriate person to just say a few words to introduce him. Malta.
Yeah, thanks, Luke. Yeah, so it's a great honor and pleasure to announce today's speaker, Mike Meylan. He's a professor at the University of Newcastle, and well, most of you probably know him, but just a few short words. So, before moving to Newcastle, about roughly 15 years ago, Mike spent his career in New Zealand. And he's very well traveled, having spent a long time research sabbaticals in several places, including Oxford, Cambridge, Paris, and he's a live member of Clare Hall, one of the colleges of the University of Cambridge, and the list goes on. So I'll stop here, just mentioning one more thing, which I think he's done a great service to the community, which is being a co-founder of KOZWaves, the conference series. So without further ado, I'm very happy to see you, Mike, and very curious and looking forward to your talk on solving the wave equation using the Helmholtz solution.
Okay, thanks very much, Malta, and it's a great pleasure to talk, to give the presentation. All right, so let's just, I'll just get started here. Why have you not moving to the next slide? All right, so the talk's really ambitious, okay, which is very dangerous because I want to try and explain something to you, and so far I've succeeded in explaining it to about one person in the world. So that puts a bit of a challenge, but I wanted to try and give you at least the big picture of it, and it's great if we can have a discussion about it. So I'm interested in solving the linear wave equation. I'll come to a definition of what that actually is because there's some debate about it, and I'm only going to solve it obviously from my definition. And I'm going to give so the idea is trying to solve it in the time domain. So one of the things is that I'm going to be a little bit bold here. If we type into Google and we go separation of variables wave equation. So this is, and then we get this first hit here. So we're talking about the wave equation of separation of variables. So this is something that I'm hoping everyone knows about. And we go down along and see what these guys have done.
You can't see your browser, Mike.
Oh, you can't see the browser. Okay. What have I done here? I'll stop sharing and I'll try and share the share screen to share. Okay, so can you see the browser? Let me see if I can grab it here. What the heck's going on here? Can you see the browser now?
Yep, now we can.
Okay, brilliant. So that's the solution.
Is that, yeah, so that's PDF, but anyway, yeah, we can see that.
Yeah, I've just randomly gone onto the wave and I've found the solution to the wave equation. And we look here and we find the solution here, and you notice it involves time. They solve it in the time domain. They get a solution like this in the time domain. So that's my goal, is to show you how you can do that for these problems that maybe you weren't aware of. And this actually fits within the paradigm of what I'm going to do, what they've actually done here. Okay, there's a lot of maths that I'm going to talk about that maybe they don't know about, but I'm going to try to show that you can construct the solution in the time domain. You don't need to just solve the Helmholtz equation. But certainly when we start out solving the wave equation, we do solve it in the time domain. And then at some point, it sort of becomes tricky. This is at least my impression. And then we just solve it in this, in the frequency domain, this Helmholtz equation. All right. So let's crack on here. So this is really important. So we start out with an abstract wave equation, which is of this form here. So it's the second derivative of something which may be a function or a pair of functions or something like that, plus some operator, which I write as a squared times eta equals 0. So A is a positive self-adjoint operator with respect to some inner product. So this is what a wave equation is, as far as I'm going to define it. And then I'm going to talk about how we can solve these equations. So I write a squared because it's if it's positive and self-adjoint, we can find the square root of that operator, and that will appear as well. So for your standard wave equation, a squared is just minus d by dx squared. And you can work out what the square root of that's going to be. It's going to be I times the derivative. All right. And then for the standard wave equation, the inner product is just the integral of, and I've got a comma here, which is a typo, but of eta times eta prime, it's just the integral. And over some space d. So the question is, if we've got basically almost all the problems that people are solving fit somewhere into this paradigm, the only thing is it's the positive self-adjointness is highly connected with energy and with conservation of energy. So if you have a system that doesn't conserve energy, it's not going to fit into this framework. So it needs to be energy conserving. And it's obviously linear, okay? None of this theory would work if the waves are nonlinear, all bets are off. The other thing is this actually encompasses slightly more than the what we consider to be a wave equation, because in the simplest case, this is just simple harmonic motion. All right. So I'm going through this in the abstract way, because this abstract maths kind of helps us to understand it, but I'll try to bore down into some examples later on. Okay. So here's the point. When we solve this wave equation, we have to specify the initial conditions. We have to specify what the value is at time t naught of the function and what its time derivative is. We have these two initial conditions. And once we know that, we can then specify what the solution is forward in time, some time step. And so what that defines is a group of operators, a single parameter group, that takes the solution at some time and maps it forward to the next time. And if we go back to these good old guys from UBC, wherever the hell they were, did I delete them? All right, but that separation of variable solution, that's exactly what they found. They've constructed this one parameter group that maps a solution because they have to feed in these initial conditions, and they've mapped it forward to some time. Now, my theory is that this is the most central object in wave theory, this one parameter group that takes a solution and maps it forward. It takes a solution at now, and it tells you what the solution will be in 20 seconds. And of course, it simply forms a group, because if I want to know the answer in 20 seconds, I can apply the operator for 10 seconds and then apply it again for 10 seconds, and that must be the same. So as I said here, for the simple solution of the wave equations, that's exactly what's found. So when you do separation of variables, you compute this operator G. But no one thinks about the operator or writes it down or et cetera, because that's too abstract and too mathematical for to be introduced at that level. Okay, so the question is, how do we find this group and how do we calculate it? Now, one of the motivations for this is that it's really, really easy to do this. It's really easy to calculate. Like, it's not a difficult computation. I was visiting someone, and I was explaining to them that you could do this calculation in the time domain, and they gave me and I said, calculate the frequency domain solution that you've found and just send it to me, and it's a MATLAB file, and I'll do it. And the person said to me, I was amazed it took you an hour, and I was like, yeah, well, that was because I made some stupid error that took me half an hour to figure out. So it was very, very easy to compute this, and I found exactly this G. All right, so just a quick point here about the formal solution to this equation, because I'm going to break this up and go a little bit more abstract, but at this point here, we can solve this by calculating cos of this operator A, whatever this abstract operator is, times t, and that's our operator that acts on the initial value of the data, and then this is the operator that acts on the time derivative. So this is the solution written down in a formal, totally abstract way. You can see what happens here. I differentiate cos twice. with respect to t, I'm going to get a squared, right, from our differentiation rules, and I'm going to get a minus. That's going to cancel a squared. And the same with my derivative here. And of course, it's going to recover the initial condition of what t equals 0, sine will be 0. And if I take the time derivative, this will become cos, they'll cancel. And this is precisely in that damn separation of variables solution, which I stupidly deleted. You can see cos of time appearing and sine of time appearing. You can see all these things appearing. That's exactly why it looks like that. So this is just in an abstract notation, I've just written down the solution that you find from separation of variables. All right, so this doesn't take us to this evolution semi-group, this evolution group directly. It's kind of buried in here. There's reasons why, like as always, it's generally not a great idea to use cos and sine. You're better to use complex exponentials. We've worked that out, right? If you look at very ancient papers, they'd have cos omega t plus some amount of sine omega t with a phase or something, and then we realized let's use complex exponentials. It's more powerful. But that's going to cause all kinds of confusion to the students when you teach them separation of variables. And sometimes this is actually, you can just, computationally, you can find cos of the operator. Once you can find, we're going to define a calculus where we can find any analytic function of the operator. So we can do cos, we can do exponentials, right? We can do whatever we wanted. All right. So the next step is to break this apart. It makes a lot of sense to do this. So we just rewrite this operator as in this two-component system with this matrix here, and we put a few i's in, which are always helpful. But you can see what happens. The time derivative of eta is just the time derivative of eta, and this is equal to a squared minus a squared, right? When I multiplied out, it's just a simple, I've just rewritten this equation in its two-component form, just like you do, in MATLAB if you wanted to solve it numerically. And then this matrix is inner product is self-adjoint in a new inner product space, which involves the operator A. Notice we've taken the square root of this operator that appears here. And this is really interesting in itself because this is the kinetic energy, this is the potential energy and this is the kinetic energy. And you can actually, the equipartition theorem that says these two are equal just falls out of here in this abstract way. You know how one of the beauties of maths is if you abstract far enough up, everything becomes very simple and clear. Like the self-adjointness and everything's really simple here once you've gone to this level of abstraction, and you can actually easily see that there's going to be an equipartition here of energy because you know this relationship between these terms here. You can shift the a squared across, get the second derivative of time. You can shift the time across here. All right. And then so we've got the evolution semi-group is just the exponential of i minus i times this operator. And there's the semi-group. And of course that immediately the group. You immediately see why it's a group because, exponential of, you add. So all we've got to do is calculate this thing here. Now that looks totally scary and we don't know how the hell to calculate it, but we have this. We know that the a squared is self-adjoint. We know that this operator here, more's the point, is self-adjoint. So we can use the spectral theory to understand and to calculate it. So what's the spectrum of this operator? Well, the spectrum of this operator is just the solutions to Helmholtz equation. I should have put an omega here. Actually, I just see it's a typo. Because it's a bit funny to index on K and omega, right? But I suppose it's fine, either the IKT, we normally use omega. So this operator self-adjoint, so the spectrum of it has to be totally real. And because it's positive, it also has to be positive, right? So we end up with the spectrum being omega squared or K squared as I've written it. So the spectrum of this operator is just the solution of Helmholtz equation. In the case of wave equation on a string, which is a finite length, then the spectrum is just the values of the you get out of the separation of variables. So and then the Helmholtz equation solution just plugs straight in here, and this is what the eigen functions they have look like for the in this two-component form. So essentially, we've got to calculate this strange object, this group, that we're going to do, and we're going to do it by using the eigenfunctions of this operator, which turn out to be the solutions of Helmholtz equation that you've solved. So you probably have never thought about it as an abstract wave equation, maybe, but you've definitely calculated these. All right. So the easiest way to think about this is that we're generalizing the Fourier transform, but we define a transform built out of the solutions of the Helmholtz equation solutions, which are the eigenfunctions of this operator. So this is if they're discrete, we get a kind of generalized Fourier series like a Sturm-Liouville, and if they're continuous, we get a generalization of the Fourier transform. So we get this mapping between the two spaces. And so we calculate f hat of k, and then this is the inverse of the operator. So I've written this integral from minus infinity to infinity, but it could be a sum over some discrete space. I'm just assuming that we've got an infinite spectrum. We've got like a standard wave equation, which every frequency is allowed to exist. So all of the stuff looks horribly abstract at this point. But it turns out that you can compute, just like the Fourier transform can be computed by a matrix multiplication, known as the fast Fourier transform or the discrete Fourier transform. In exactly the same way, this transform can be really well approximated by matrix multiplication. So effectively, this is just going to reduce the entire solution down to matrix multiplication. Okay, so, but we transform with this, and we end up in this f hat of k, and the f hat of k just evolves as e to the ikt. So one way to think about this is this numerical approximation of it. So this A becomes a matrix. So we can, which is self-adjoint. So we can write the equation as, we can find the eigenvalues and eigenvectors of this matrix. But one of the things that's even better is that we don't need to solve an eigenvalue problem. We know the eigenvalues and eigenvectors because we know that they're going to be well approximated by this eta hat of x and k. So it's a bit, normally normally in something like the finite element method, you go to a matrix approximation and then you compute the eigenvalues and eigenvectors of this matrix. But we assume we know the spectrum of the matrix of the operator, and then we approximate it by a matrix. So we never need to compute eigenvalues and eigenvectors, which is a really expensive computation, and it's got all kinds of problems. It's not super stable or anything like that. But we eventually very naturally end up with this with the diagonalization. So the solution can just be written as matrix exponential of a diagonal matrix multiplied by the same matrix, but conjugated, complex conjugated, complex transpose. And these are just built directly from the solutions of the Helmholtz equation. All right. So what we've done, a whole lot of crazy abstract maths, which with like symbols, but which once you learn to move them around, everything's really easy. Because when you get down to the actual brass tacks of a problem, even just showing self-adjointness can be an absolute nightmare. And then I've shown how from that we can end up with an approximation of the solution built out of these frequency domain solutions. So let's have a look at I'm going to go through a couple of problems, one of which is simple. I could go through the solution for separation of variables or waves on a string in this context, and I decided not to do that because I think it can sort of be off-putting if people see a simple problem made incredibly complicated, but it's a great exercise to do to try and put that problem in this context. But let's have a look at this equation here. So this is just a typical wave scattering problem where you've got and I've written the equations down in the time domain, but if you went to Helmholtz equation, which is, this is like scattering from some rigid objects. It's just a simple problem in water wave scattering. So you'd have I omega or minus I omega times phi is equal to, and you'd have minus I omega times zeta is equal to, and you get the standard sort of free surface condition. So this is the equation for linear water waves, right? The ones that we were talking about causing havoc on the beach. But we've got some bodies that scatter. So how do we place this into our scheme? Well, we introduce this operator, which essentially, it's maybe easy to see it here, but we essentially maps what happens on the surface, the potential on the surface to the normal derivative by solving Laplace's equation. So we introduce it here, and we define this here. So it's a Dirichlet and Neumann map of the surface. Okay, there's a lot of notation here, but essentially, if you know the potential on the surface is going to tell you the normal derivative, and then the equation can be written in this abstract wave equation where this is the operator a squared. So notice it'd be really a nightmare to try and find the square root of that. Like, what the hell is that? But we actually can operate with that because once we go to the spectral representation, we can just calculate it. So we don't really need to know the form. We just know we can take a square root of that. It's far from obvious, perhaps, that you could do that. And then the inner product space is just this, I don't know why I've written here, this plus, this is an error, it should be equals. It's just an integral over the free surface of the two functions multiplied together, just the standard. So you got to be slightly careful. It's not minus infinity to infinity unless there's no body on the surface. If there's something sitting there, you just exclude that part of it. And the eigenfunctions of this operator are just, this is the Helmholtz solution, is just where this is, you know, there's a would normally be a minus omega squared here, but there's because of the sign, it's that thing there. Okay, and you've got waves coming from both directions. Okay, just adds another level of complexity to it. Okay, and there's the solution. I've written it down here in terms of this cos and this sign. But in fact, what you do when you want to compute this is you just form up. So this is, maybe this isn't super important, this way that to formulate it. Let's just have a look at how you can actually compute it. So there's the expression that you want to calculate. I've written it in terms of cos here rather than the exponential, but you've got to take the initial condition and you've got to inner product with your waves that are coming, the incident, and then you're going to multiply it by cos omega t, and then you're going to multiply it by these same waves. So this inner product is a matrix, is an integration, but it's actually it's really this matrix times this zeta naught. So if you set up a matrix that's just the values of the so you imagine in your MATLAB code, you just have x running one way and the frequencies running the other, and you just form a big solution that's the solution on the surface for all these different frequencies as a matrix. Then the solution is this matrix times f times cos omega t. Okay, now omega, that's the diagonal matrix, times this conjugate of this matrix. So you don't even need to store the matrix, the second matrix. You never need to create this. So you just create this one matrix, and then you do some matrix multiplication, and you get the solution at every time. When you look at this solution here, you see something really remarkable about linear wave equations, because I feed into this the solution now at t equals 7, and I'm going to now calculate it at every single time out to infinity and back to negative infinity. I know all of that. So a linear wave equation, once you know the solution now, you know it for all time forward and for all time backwards. So it sort of tells us that the world isn't totally linear. But it just reduces, once you discretize it, it reduces to this matrix multiplication. And of course, somewhere buried in all of this has to be the Fourier transform, the FFT, right? Because that's the wave equation is basically built around that. And there's some version of it where this whole thing would reduce to the fast Fourier transform. So this P would be the fast Fourier transform. This would be the inverse fast Fourier transform. And that's why you get this 1 over n appearing here. And this A can be, the A depends on how you discretize the spaces, but you can organize that to be 1 as they do for the FFT. So we've generalized the fast Fourier transform in a sense. We've generalized the Fourier transform, and then we've said, okay, we're going to generalize the fast Fourier transform to do this computation. And the main idea is that we're doing this integral by some very simple discretization, exactly as is done for the FFT. Like when they go from the Fourier transform to the FFT, there's a lot of, they don't overthink it. They just take, and there's no special, the quadrature rule is the most simple one you can possibly imagine. It's the midpoint rule, etc. But that's actually seems, there's good reasons why that works. And all these fancy quadrature rules are just complicate it and add unnecessary calculations. All right. I'll just show you some pictures of the sort of thing you can generate. Uh-oh. This was working before. Just give it a few seconds. This will be very disappointing if these don't run, but just to show you, one of the weird things about this method, this numerical method, is that I said to you, it produces a solution from the solution at t equals 0, it produces a solution for all time forward and for all time back. So when you ask it to produce a solution at t equals 0, so you feed it in the solution at t equals 0, and then you ask it to compute it for t equals 0, you will not get back what you fed in, and you can actually tell how accurate your solution is by how accurately it reproduces the initial condition, which is a very weird thing because it's not very clever to be able to tell what the solution is now. You know what I mean? Like predicting the stock market now is of no value. Okay.
Putting your slides down and opening them up again, Mike.
Yeah, I think that's right. It should do. Just reopen the. Yeah. I'll have to tell a joke while we're here. Because I did not a joke, an amusing anecdote on predicting the future, but I decided sometime last week, I thought Trump's about to crash the US stock market. I've got to get my pension out of the US stocks, right? My super. So I went and I got on the website and said, I'm going to change my, the allocation of my money. And I went and filled it out. And then I knew it wasn't going to happen instantly, but I woke up the other day to find the stock market had crashed, and I logged onto the website and to see, how it had all gone, and they said still pending the change. So unfortunately, being able to predict the future 6 days ahead or whatever wasn't any use. Okay, what's happening here? If it plays. Yeah, here we go. Okay, brilliant. So this is just showing you the kind of calculation you can do. So I've sent in waves of all different frequencies into this. So imagine this is a little, so short frequencies are going to be scattered by this terribly long frequencies are going to pass through it. So, and I've calculated it from both directions. Okay, from symmetry, I didn't have to do that. And then I've used that to build myself a huge matrix with the solutions at the surface for all the X points and for all the frequencies. And then I've just done a couple of matrix multiplications to produce that surface. And you can see that they're actually, if you looked at the initial condition I told it to reproduce, it didn't do such a brilliant job because there's a lot of very high frequencies and all kinds of nasty things that go on with that. All right, this is going to play. Yeah, here we go. You can see this curling at the end. That's actually a numerical artifact. I could have actually fixed that, but I've left it in there just to sort of show it. Again, it's because of this. There's this, and you can see lots of cool stuff happens here because you can see it transitioning to trapping and things like that. But it's just come straight out of the solution of the solving it in the frequency domain. You can solve it in the time domain. All right. I want to do one last problem, and I want to go through it just because it's quite interesting, and it shows you the level of abstraction that you can run to. Here's them being submerged, so most of the energy just pulses off as two pulses, and then there's this weird kind of trapped wave left between. All right. But it leads to these calculations, it leads to this visualization. And if you, in some ways, I think this shows more about the behavior of the system as well than, say, if I showed you the reflection and transmission coefficients, which seems to be a really common thing people plot. Okay, so what I want to do quickly is look at this problem of a floating ice shelf. I love this problem for loads of reasons. It's sort of practical and the mass of it's really cool. So you've got this floating ice shelf here. It's supposed to be the open waters here, and the ice shelf's, it comes to the end, hits Antarctica here. And it's governed by this system of equations. And I've written down phi as the negative acceleration potential, but this is so you've got this coupled system of equations between the displacement of the surface and the negative acceleration potential. Okay, which exists only, it's one-dimensional. There's no depth here. We've depth averaged out. So you can see here, this is quite a nasty system of equations of coupled PDEs to solve. So we can write it as an abstract wave equation where this operator A squared is the following. A squared acts on eta to be equal to one of these two different things. So it's the second derivative of the acceleration potential multiplied by this under the ice shelf. It's just negative the acceleration potential for x less than 0. And the negative acceleration potential satisfies this condition here. So imagine if you knew eta, you could solve this equation, calculate the negative acceleration potential and feed it back into here. So this is a very abstract sort of operator. Imagine trying to find the square root of that. I mean, it doesn't, the mind boggles, but we can still compute what the action of the square root of this operator is. That's the thing from this, because we know the spectrum of it. And of course, if we solve the spectral equation, all we have to do is substitute the minus omega squared eta is plus this strange thing here equals 0. And it turns out that's actually really simple to solve. It's just a matrix equation. But this is how, once we cast it into this abstract form, and then the operator is self-adjoint and positive in this inner product space here, where it takes into account this normal kind of energy plus the energy of the bending. It's actually a horrendous calculation to try and show that this very abstract operator here is self-adjoint in this energy inner product space. I've got, I'm not sure I've ever actually done it, but I've sent a few people to try to work it out, and they never sort of come back very happy. But it is actually, but we sort of know the reason we can even find this is because we know that this is the energy, so we know the target, so we know it has to be self-adjoint in terms of that. All right. Yeah. And then we can write it as this matrix equation here, evolutions and grid. I've shown you all this stuff before. I don't need to go through this perhaps. I'm just conscious I want to wrap up. There's a really weird thing with this mapping about the way that it preserves the this transform preserves the size of the vector. Because I sort of love the way that this, because if you think about these transforms just abstractly as mathematical objects, they preserve angle and they preserve size. So they can take its triangle and they can rotate it and move it, but they can't do anything more than that. So that's a very restrictive kind of mapping. But if you're living in an infinite dimensional space, they can do all kinds of crazy stuff while still preserving the size. But here's the thing written, we approximate this integral by the sum over the points x. This is the key idea. So every time we see an integral, we approximate it by a sum, and these are just the Helmholtz equation solutions. And there's the solution written out in terms of the Helmholtz equation solutions expressed as a matrix. This is, I just wanted to show this quickly because it just shows you the MATLAB code, the way that it works. Just to get a sense of how, because it's ultra simple to code. Nobody wants to write complicated code, but you've got this displacement water store and displacement shelf store. They've stored the solutions for all the different frequencies and spatial points as a matrix. So you multiply that. So this is a matrix times a vector. This is the initial condition. And there's a little bit extra you have to add on here because of the way the inner product involves its fourth derivative and stuff. And then you divide it by 2 and pi, okay? Because pi, that's always going to appear. And then when you want to calculate, so you only have to do that calculation once, just like calculating the Fourier modes for the initial condition. And then to calculate the solution at a later time, you simply just multiply it out and then you multiply this exponential by the initial condition here. It's just and this is just a dot multiplication because it's a diagonal rather than forming a diagonal matrix. So it's actually really quick to compute as well, because of course computers love doing matrix multiplications. And you can see here how this if you know anything about MATLAB, this dash here conjugates and transposes. So it's one of the only times. Normally that's the most annoying thing in MATLAB, because we actually only want to transpose, but here we actually want to conjugate and transpose. So this notation actually helps us out. So that just gives you a sense, just looking at that if you've got your solution, just in the Helmholtz equation, if you form it up into a matrix, we just start matrix multiplying and produce the solution. So I just show you this solution here. This is the ice shelf. Okay, I've got it on the other side now than I had it in the previous picture, but let's not worry about that. So this is some initial pulse starting here. So it's going to break into two pulses. I believe this plays. No, sorry, I organize it to be flowing to the right here, to the left. So it hits this, and what are you doing here? See if it plays again. I don't want to put it on full screen mode in case it crashes the computer, but yeah, this is quite good. So there's a pulse traveling. It's all shallow water equations, and then the pulse runs into the this is the sort of simulation, the time domain that you can do. I mean, it makes a great movie, and it sort of visualizes the behavior of the system. So the ice shelf's excited, and you can see the kind of elastic bending of this thing here. So this is the way, and real ice shelves in Antarctica are much more complicated than this. So they're moving it with this kind, but they are constantly in motion. It must take a kind of form like this, which is kind of bizarre, the way it looks. And then this is what happens if you put if you bend the ice shelf. So this is a bit dangerous, because this is not an experiment I want any of you to go and conduct. But if you went down and let a nuclear bomb off under an ice shelf with something and you started to bend it like that, but we can mathematically do that. And you can see here, this is kind of crazy what happens here. I really love this, because there's just so many crazy, this is completely deterministic. This entire system is completely determined. I mean, I told you I can calculate it for all time out to infinity and back. It's the most linear deterministic system ever. But what appears out of the ice shelf is this bizarre kind of wave that looks, this thing here is an artifact of the plotting. It has to move constantly, but it looks like a stock market. There's no way that the system, I mean, you're getting this incredibly complicated waveform being formed from this deterministic system. So this is, and you can see this thing here moving here. So, it gives you a sense of, the kind of complexity of the mapping that it's trying to represent, because it's actually taking the solution from one space and moving it into another, where it's actually super simple. Like the craziest part of this, which is very hard to conceptualize, and I haven't even touched on it, is in the process of this mapping, you actually send it to a space where this evolution operator that you see there acting just acts as a shift. So it turns out there's an enormous class of functions where you essentially can map to another space, and it just becomes D'Alembert's solution. And this is actually one of those systems. It's hard to conceive of how this mapping would send every single thing you've seen there to the same point, only shifting it. That's the mapping that's actually being constructed. But I think it's better to conceptualize it as a very practical way to calculate the time-dependent solution from the solution. Once you've solved Helmholtz equation, then you just, as long as the system's preserving energy, which means r squared plus t squared equals 1, then you can apply this formulation. All right, I'm going to finish there. So I've gone a little bit over time, but thank you very much.
Oh, great. Thanks, Mike, for this very interesting talk. I presume there will be loads of questions. So anybody, maybe I just start, Mike. So so from a practical point of view, assuming that you've computed that you can compute the time harmonic solutions, you never really need that abstract operator, right? Because all you need is the diagonalized form, which is what you've computed. But do you actually need?
No, you need the no, you don't. You don't need the abstract wave equation, but you need that in a product in which it's self-adjoint.
That's what you need it for, right? You need that. That's the key thing, right? That's why you need this additional add-on stuff so you can create the correct inner product.
Correct, because for example, if you want it, it's got to account for the energy. So if you had something that's moving, your space suddenly gets appended by this one-dimensional object, which is the motion of the body, say in heave, but that contains a lot of energy, and you've got to account for that energy. Yeah. So exactly right. So when this whole theory was developed without working out that this is abstract wave equation and about breaking it out, like that's something that's come to me. I've come to see that the advantage of that is that if it fits into that paradigm, yes, you can do it. That's all you require.
It's very neat because, I mean, just generally speaking, it's quite clear that you can assemble any solution from the time harmonic solutions, right? But then the question is, how do you assemble them in such a way that you fit the initial condition? Because that's what you want,
correct.
And that's exactly
that's exactly right.
Exactly.
Because exactly like the Fourier transform, you try to write down some initial poles as all these infinite waves. You never believe that's going to happen, right? Makes no sense you can do that, but it turns out you can. And the Fourier transform tells you exactly how to do that. And this is the same thing. Yeah.
Yeah, no, very, very nice. Further questions?
So we can't see everyone on here. If you want to ask a question, you can put your hand up or just feel free to unmute yourself and go ahead. Okay, so what we're going to do is we're going to have another announcement now, just quickly, and then we'll come back again and we'll open a discussion and see if anyone has thought of any questions for Mike. So at this point, I'm going to ask Chandru, are you there?
Yes, sir.
Would you like to make your announcements?
Yes, sir.
Do you want me to stop sharing?
I think so, Mike. Yes, if you would.